Carbohydrates are a complex and a simple subject. Haha, that's a pun on simple sugars and complex carbohydrates. We'll see that shortly. In the big picture, photosynthesis that produces sugars from carbon dioxide and water is probably the largest chemical reaction on the planet. Plants capture sunlight and through the process of photosynthesis reduce carbon dioxide to sugars of the empirical formula C6H12O6. We're going to see that this gets much more complicated. And these simple sugars, glucose for instance, can then be made into cellulose and starch. And a simple stereochemistry at one position is the difference between starch in things like potatoes and rice, which have huge caloric contents for people, and cellulose, which has one stereocenter different but is a whole bunch of glucose molecules stuck together in a way that we can't digest it. So it has no caloric content, and it's called fiber. Of course, plants and those fibrous bodies became coal, oil, and natural gas that we burn and oxidize back to carbon dioxide that supplies the energy. And this is one of the key things. We can't wait for the plants to do it again. We've got to find ways of capturing sunlight and storing it efficiently. All right, key thing to go back and review for this chapter, chapter 25 in McMurray, is the Fischer projection. Okay? In the Fischer projection, remember the horizontal line, the two substituents, you can think of them as on a wedge coming out at you. And the two substituents on the vertical axis are going to translate into pointing away from you. And you need to be able to assign chirality. From the Fischer projection. All right, so let's start with the simplest of the carbohydrates. The first of these is glyceraldehyde. Okay, 3 carbons, 1, 2, 3, an aldehyde functional group, and 2 alcohols. You also, I hope, recognize that it has a chiral center. These things can be measured by optical rotation. Glyceraldehyde is the parent of the aldehyde carbohydrates that we'll be looking at. It is also a part of a class called Aldo trioses. Aldo for aldehyde, tri gives us is the 3 carbons, and os tells us it's a sugar. Okay, so this is about the simplest of the sugars. So all of the Aldo Hexoses, which we're going to see are very important to us, derive from this. The keto trioses, of which fructose is the most significant, come from dihydroxyacetone, which is of course achiral. Okay, again, review those if you don't see that right away. All right, so let's look at these classes of molecules because I want you to be able to classify the molecules. Aldoses, they have an aldehyde. Ketoses, there's a ketone. So here's an aldo, 1, 2, 3, 4, and a keto pentose, 1, 2, 3, 4, 5, and it has a keto functional group. That's the classes of molecules, and we'll continue. The C6s, okay, would be, for instance, the Aldo Hex for 6 oses. Okay, the Aldo Hexoses, those are going to be some of the most significant. Now let's look at something specific here. We saw glyceraldehyde a minute ago. Of course, that's R plus glyceraldehyde, and in the Fischer projection we draw this on the right, and so we're going to have this designation D because they're dextra, well, they are dextrorotatory in many instances. This is the R plus, which makes it dextrorotatory, but the capital D tells us that it's the group of diastereomers that has the OH in the penultimate carbon, so we would number this 1, 2, 3, 4, 5 with the OH on the right. Okay, so ribose. Why are we interested in ribose? Because of DNA and RNA. deoxyribose ribonucleic acid in DNA, so it's lost one of its hydroxy groups, and ribonucleic acids in ribose, so it has not lost that hydroxy group. Okay, perhaps the most famous of the carbohydrates is glucose. Blood glucose levels are important in diabetes, for instance. And fruit sugar, this is fructose. So these are what we call the linear forms of these. They're drawn in the non-cyclic form. Okay, so a couple of more quick things. The D series, okay, again we started from glyceraldehyde, but we started from the R+. We could derive the diastereomer. In fact, the mirror image of glucose is L-glucose, but it's not naturally occurring. So what's naturally occurring is D-glucose. There is, of course, a mirror image of all these molecules that I'm going to draw, or that we're going to see illustrated today. But the D series are the naturally occurring ones. All right, so let's take a look at these now. So this is something that I want you to learn and to know, the Aldo Hexoses. Starting from glyceraldehyde, we can start to add a carbon. Okay, so here's the glyceraldehyde. We add a carbon first on the right and then on the left. That gets us erythrose and threose. We add another carbon to erythrose first on the right and then on the left. We're at ribose, arabinose, xylose, and lixose. I came up with a mnemonic for these, Raxil. These are nonsense things. Then you may have heard the mnemonic for the Aldo Hexoses. Right? So here are the Aldo Hexoses, and you should know these. It's going to be important in your biochemistry classes, especially if you want to go into professional schools. All right, so here we go again. We have allose, altrose, glucose, the all-important glucose, mannose, gulose, idose, galactose, and tallose. There's an acronym for this. It's called all altruists gladly make gum in gallon tanks. Okay. Allose, all. Altrose, altruists. Glucose, gladly. Mannose, make. Gulose, gum. Idose, in. Gallon, galactose, tanks, tallose. Okay, so and now notice the pattern. All hydroxyls on the right, one hydroxyl on the right. Okay, then we switch these, one on the left here and then one on the right and one on the left. But this one stays the same between those two because they only change at one stereochemistry position here. Then gulose, we move down one in the carbon chain. We have the OH on the left, the OH on the right, and then these two switch back and forth for gulose and idose. So there's a pattern there that you can easily recognize. It would be good to know these. Let's take a look at these and think about the stereochemistry for just a minute. So this is a slight modification of that Fischer projection so that it's easy for us to see. The D designation has to do with where that OH group is. In the Fischer projection, it's on the right in the D series, and it's on the left in the L series, as I've already suggested. Now, thinking about this, we have 1, 2, 3 stereocenters. Stereocenters go as 2 because there's an R and an S to the end. So that means we have 2 to the third or 8 diastereomers for this, or stereoisomers for the aldo pentose. The same for this ketohexose, 1, 2, 3 stereocenters. Now, if we went back to the aldo hexoses, we have 1, 2, 3, 4 stereocenters. 2 to the 4th is 16. We have half of those pictured here. The D series, of course, the mirror image of each one of those is the L series and the other diastereomers. Now, there's another thing that's important for us to remember. We very recently covered the reaction of aldehydes with alcohols to make acetals. And of course we do this by going through a hemiacetal. Well, notice what we have here. We have an aldehyde and a ketone group in the presence of lots of alcohols. So what happens with these is that they actually cyclize in solution. So here's an example of mannose, the linear form that we've drawn before. Then they've drawn it in this sort of pre-Hawthorne projection here. We'll see Hawthorne projections in a minute. This can cyclize, and so now we can have OH up or OH down. So the OH can be here and the H there, or vice versa. What functional group is this? Well, we have a carbon-oxygen-carbon ether linkage, and we have a carbon-oxygen-hydrogen alcohol linkage. This is a hemiacetal, and this chemistry is very important in biology. Because one of the key things I want you to remember from this is if we have a sugar that's in the hemiacetal form, here's the hemiacetal form, it's called a reducing sugar. And those who teach biochemistry, it's very important for you to recognize the difference between a reducing sugar, it's a hemiacetal, and a non-reducing sugar. That is, the linkage is a full acetal, that is ether linkage, ether linkage. So if there is any one hemiacetal anywhere in a complex carbohydrate, it's still a reducing sugar. That's an important one to know and to recognize. Now, from a chemical standpoint, these, because they're in equilibrium with the aldehyde form, will give a positive test for using, if we use Tollin's reagent. But those with only acetals, they're not in equilibrium with the aldehyde, so they don't react. Again, the chemistry here is very important. All right, so what you notice here is we've drawn this in a chair six-membered ring. Now, do you remember cyclohexanes and all of the issues with that? I hope so, because this is one of the reasons we wanted to know and understand that. As you can see, we can have an equatorial or an axial substituent. Here again, equatorial, equatorial. So if I were to draw in the hydrogen there, there's the axial hydrogen at the 4 position, the axial hydrogen at the 3 position, the axial hydrogen. Okay. Now, let's look at these in a little more detail. Here is our Fischer projection. Remember, it looks like this. There's the dash and the wedge. Then there's the Hawthorne formulation, and you should be able to recognize and interpret a Hawthorne projection. Here's our hemiacetal. This is what we call our anomeric carbon. That's the carbon where the OH can be up or the OH can be down, and of course it's in equilibrium. Okay, and so this is glucose, and when glucose is fully cyclized, that 6-membered ring with an oxygen in it, we'll look at this in a more. This 6-membered ring is called pyran. And so this is the pyran form of glucose. Ose tells me it's a sugar. Gluco here is short for glucose and tells me that I'm dealing with glucose and all of its stereochemistry. The difference between alpha D-glucose and beta D-glucose is the anomeric carbon. So I always remember this as beta's above. So there's my 6-member ring plane. The OH is up here, and the OH is down in the alpha position. All right, and this stereochemistry is going to be very important for us, for instance, for the difference between starch and cellulose, because both of these are polymers, long chains like a train with lots of glucose molecules stitched together. But in one, the starch, we can digest it. In the other, you have the opposite stereochemistry at this anomeric carbon, and we don't digest it in its fiber. Okay, so let's look at a unique property about glucose really quickly. If we take glucose in its crystalline form and dissolve it in solution, it's in equilibrium. At equilibrium, we get 37% alpha D-glucose, 62.6% beta D-glucose, and there's a tiny trace amount of the linear aldehyde form. But when it crystallizes, it comes out in one form. And so Glucose undergoes what we call mutarotation. You dissolve it, you get one optical rotation, and over time that changes. It changes as this comes to equilibrium. All right, so important properties about glucose. This goes back to all that acetal chemistry, alcohol chemistry, and things we've learned already. Now, I mentioned a moment ago about pyran. There's a 5-membered ring. In fact, maybe you've heard of the solvent tetrahydrofuran, where there are 1, 2, 3, 4 more hydrogens. But like we had the 6-membered ring form of glucopyranose, we can make the furanose forms of these. And there's a very important one that I want you to know, and this is ribofuranos, because this is the cyclic form that many of you have probably seen before. Here's our anomeric carbon, and so for instance in DNA, the nucleic acid bases get connected at that anomeric carbon. And of course, so this is DNA and RNA, so ribose would be an R. All right, now to finish up here on chapter 25, I want to come back to a small part of this starch versus cellulose. So if we break up starch which has as many as 3,000 glucose molecules in one starch molecule, this is maltose, which is the disaccharide of starch. So this is a disaccharide, right? Glucose itself would be a monosaccharide. Oops, I'm moving things around. You can have trisaccharides and polysaccharides. So starch and cellulose are polysaccharides. So in starch, which we digest, potatoes, French fries, rice, corn, all of these things are high in starches. There is an alpha linkage. So here in our 6-membered ring form, again, that's the Hawthorne projection. Here's the 6-membered ring projection. We have the alpha linkage. So the enzymes in our body can digest the alpha linkage. Now you may know that cows, for instance, do eat grass, but it's actually their microbiome, the organisms that live in their tummy. You know that cows are ruminants. They chew their cud, for instance, and then the bacteria and organisms in their gut digest the cellulose. So here's the difference. Cellulose, and I'm going to focus here on the 6-membered ring form, from that 1, 2, 3, 4 prime to the anomeric carbon, it now has a beta glycosidic linkage. So this is a depiction of what's called cellobiose. So if we digest cellulose down to its disaccharides, we get cellobiose. Cellobiose is almost identical to maltose. Maltose is a sweet sugar, lots of calories. And the difference here, I want you to see them now side by side. We have a beta linkage in cellobiose, and we have an alpha linkage in maltose. And that's the difference between fiber and sugar.